Truncation errors. Truncation errors are those that result from using an approximation in place of an exact mathematical equation or procedure. Now we can go back to our problem, jumping problem. As you might remember, on the right-hand side, you see an illustration. A man jumps from a balloon, and there was a solution. There was a development, mathematical development for this physical system, physical mechanism. There were two types of forces: upward force, due to air resistance, and downward force, due to gravity. And we have formulated this. The differential equation that describes this mechanism, where we try to estimate the velocity, terminal velocity of this man at any time instant t after jumping. The initial speed was taken 0 meters per second, so stationary. And from physical principles, we were able to write this differential equation. The time derivative of speed is equal to the acceleration due to gravity, and the direct coefficient divided by the mass of the man and velocity squared. So this is a mathematical procedure, and truncation errors occurs when we make an approximation to this equation. So here, for example, we have a time derivative, and we have studied numerical approximation to this time derivative of velocity, and we have shown that this time derivative, time differentiation of velocity can be written in terms of the values of the velocity at two time instants, the difference between these two time instants divided by the time difference. So delta V over delta T. So there is an approximation here. Whenever we do such approximation, we'll have errors, and these errors are called truncation errors somehow. Why? Because when we do this approximation, actually we somehow ignore some other terms or something here when we consider Taylor series expansion. Numerically here, we make another error due to the size, the time difference here. We have already described this in the round of errors, where we do not have infinite storage or computational capacity while we are computing such differentiations. Okay, one theorem here is quite important, what we call Taylor theorem. That is a series, and it states that any smooth function can be written as a polynomial, and mathematically for any function at the value of xi plus 1 can be written approximately as the summation. So Taylor's theorem will show that Taylor's theorem somehow is used to estimate the values of functions once we have some previous values, given values. Okay, let's see Taylor series then. Okay, we start with the problem again. Let's say we are on a mountain, or let's say hill. We are staying somewhere here, and we are moving downward, okay? And we do not know the terrain, we do not know the slope, but we feel that this is somehow going down. So the slope is increasing with the distance. Let's say the initial position is xi, which is 0, and the point that we'd like to go is xi plus 1, let's say 1, and the difference is h. Okay, now we'd like to move on this curve and then try to understand how Taylor series are used to estimate the values of the function at any time instant here. Okay, this function here is a polynomial, and somehow this represents our curve here. The zero order approximation to this problem, I mean, we'd like to get the value of f at xi plus 1. Okay, we may do an approximation, and by considering this series expansion, I can write the function at xi plus 1 as approximately equal to the value of the function at xi. Okay, that is an approximation, what we call zero order approximation. And then we'll get this value, which is the same as this one. This is first order approximation, which means that I take the first term here. Zero order approximation, sorry. I take the first term here, which means that I take this function as a constant, not this polynomial. I simply take this polynomial as constant. Ignore all these terms. Okay, just take this constant. Okay, the next, I can include the next term and take two terms here, which is first order approximation, which means that I have to calculate the slope here. Okay, f prime of xi. So I have to find x prime, the derivative of f x at xi. If I use this, then I can simply determine the slope here somehow. Okay, and using this slope with this h, I can write down the value of the function at xi plus 1, which is the value of the function at xi plus the slope of the function times the step size h. Okay, so we got this value then. That's the next approximation. Zero order gives us the same value. First order gives us the value, previous value plus slope times the step size. We can increase this. Let's say I may consider a point here. Imagine that we are here. Instead of taking first order derivative, I can take second order derivative, which means that I have to determine the first order derivative when I go one step back, and when I go one step ahead, and measure the derivative here and here. Using these two derivatives, I can determine the second order derivative, and then use this second order derivative here, and then include the next term, okay, which is going to be second order approximation. So it includes the initial value at xi plus the slope at xi times h, and this second order derivative at xi, h squared. And in finding this second order derivative, we simply take the first order derivative at xi by going back one step back, and then take the slope, and then, sorry, one step back to get the slope. So let's say fb prime here and ff prime here. Very small distances we are talking about. So you can imagine that you are moving on the hill, and then you go back one step and see that the slope when you are going back is smaller than the slope when you are going ahead. One step further, you see that the slope is increasing, which means that we simply take the derivative of derivative. Derivative of the derivative. This delta x represents the distance. So the step size we are taking here. So we can increase this, we can add other terms. The third order, fourth order, fifth order, so it goes to infinity actually. So that's a summation from 0 to infinity. But in computer applications, we do not have infinite summation, so we have to somehow truncate this. And here in this lesson, we are simply dealing with this truncation. So let's see how to truncate Taylor series. So this is the Taylor series that we were talking about. And for any n value, we can write this as f, the nth order derivative of f at xi divided by n factorial times h to the power n. Now, after this term, we can write down this the remaining terms here, what we call remainder, as the term that represents all the values with h n plus 1. Okay, and others, n plus 1, n plus 2, n plus 3, n plus 4. As we choose h very small, then the power of h will give us very small number. So it gets smaller with each term. So at the end, it goes to 0 approximately. Okay, mathematically, we can write this remainder as the n plus 1 order of the function within xi, which is the value a value between xi and xi plus 1. N plus 1 factorial h to the power n plus 1. So this term is simply just a number. So you can imagine that we got a constant here. And this remainder is dependent on the step size, actually, h, and the power of h. And as you can see, it goes to infinity with h to the power n plus 1. And this nomenclature O, so OH, or OH to the power n, or OH to the power n plus 1. It's a nomenclature means that the truncation error is the order of this term. Okay, so this represents the truncation error simply, and the order is dependent on the step size and its power. And apparently for Taylor series, this truncation error is dependent on h to the power n plus 1, which means that if we, for example, choose an h, which is half of the, we change the step size. Let's say we take the step size as 1, and then next we reduce to half. That's going to be h over, so OH prime n plus 1 will be h over 2 n plus 1. Let me, write on this again. We reduce the step size by half here. So OH prime is going to be OH over 2 n plus 1. So OH, O H n plus 1, 1 over 2 n plus 1. Okay. So it's very important to choose here h to reduce the truncation error. So when we increase, when we reduce h, when we decrease h, then the remainder term represents smaller values, so the truncation error will be lower. When we halve the step size, simply we halve the, so let's say half the step size, simply we quarter the error, because it is simply h to the power. Okay, if this is 1 over 2, then that's going to 1 over 4. So it's very important to choose this step size carefully, but we'll be showing that you cannot reduce that much because of the round of errors. Okay, we have an example. We are given a function here, cosine x, and we'd like to determine the value of the function at xi plus I'm trying to get familiar with the drawing here. Okay, so xi is pi over 4, so we can calculate f xi, and here we got xi plus 1. So the value of the function is is given, and we have two steps, pi over 3 and pi over 4, so we can draw for simply our cosine. So something like this. This is 0, and we have pi over 4 right here, and let's say pi over 3 right here. Then this should be, I think, pi over 2. So it goes like this. This is 1. And there are two values here, then we can determine the step size as the difference, which is pi over 12. And we'd like to determine Taylor series for n equals 0 to 6. Okay. We should approximate this f of x at this value, so this one. And we are given here the values of the function at xi is given. From cosine function analytically, we can determine pi over 3, which is 1 over 2. So this is the true value. Okay, and would like to estimate this. We would like to approximate this. We can take the first order, or let's say, sorry, 0 order approximation. It says that the value of the function at the next step is equal to the approximately the value of the function at the current value. So this gives us 0.707. That is xi plus 1. That is xi. Okay, so here is xi. Here is xi plus 1. The difference is h. So then we can determine the true percent relative error. True percent relative error. The true value is here, right? 0.5 minus the approximate value divided by the true value, which gives us 41.4% error. Let's try the first order approximation, where we have the function at xi, the value of the function at xi plus the slope of the function times the step size. We can determine the slope from simply sine x, which is the minus sine x, which is the derivative of cosine. And we can write down the first order approximation. We'll get this one. Here we got second order approximation. So we got this one. So it is getting closer to the true value of 0.5. Okay, as expected. If we add other terms, then we can expect better results, of course. So let's see all together. Here you can see the values of the function. For 0, we have already determined that was 0.707. The error was more than 40%. And when we increase the order, we simply reduce the error, and at the end, when we take the value of n as 6, it gives us an error of this value. So 1/1 of million, 2.44 10 to the minus 6, which is, as you can see, very close to 0.5. So this too is quite good. Very small errors we can get here. If we add other terms, so 7, 8, then we can expect better results, of course. So let's see how to evaluate the remainder in Taylor series expansion. Remember the Taylor series expansion, the value of the function at xi plus 1 can be written in terms of the value of the function at xi. We need to know the derivatives in here. And since this goes to infinity, so we have infinite number of terms, this is not possible. It's not possible to evaluate or compute this in a computer algorithm. So we have to somehow truncate this. And we simply represent this truncation with this remainder term, Rn. And here we can take, for example, the first term. Then the function is going to be is simply calculated by using the previous value only. No derivative or higher order terms are considered. And in this case, n is going to be 0. Okay, yeah. And it includes all the terms starting from the first order approximation here. And if we approximate, if we truncate this R0, so truncation of the remainder here, the first approximation could be that we can take this remainder as slope of the function times h. So let's see what it means. On the right-hand side, we are given an f of x. We have a smooth function, and we have two values of x, xi and xi plus 1. And here the value of the function, which is given here. And here, the exact value of the function. If we use zero-order approximation, then it means that we take this as the f of x plus 1. So the R0 here, this R0, represents this error actually. Okay? So we can simply write R0, the slope of the function at xi times h. Okay, then from this truncation, we define derivative mean value theorem, derivative mean value theorem. On the right-hand side, you can see the same function, the same curve here. And this theorem states that if this f of x and its first derivative are continuous over an interval of xi and xi plus 1, then there exists at least one point on the function. So there should be one point on this curve that has a slope designated by f prime of xi that is parallel to the line joining fxi and fxi plus 1. So we determine, we are given this xi and xi plus 1 and draw a line here. And there is a point on this curve where the slope, so the tangential line at this point, is parallel with this one. Okay, so if we take, for example, another point here, let's say here, then there should be a point here whose slope is parallel to this one. Or if we take a point right here and draw a line, then there should be a point here whose slope is parallel to this one. That is what derivative mean value theorem states. And we can write this from this remainder R1 is going to be the f double prime psi over 2 factorial h squared, and the derivative at any psi, so the slope here, simply R0 over h. Okay, so this is applicable to any point on this curve, and there is just one point, at least one point, where the slope is parallel to the line that we have drawn. So we can use next Taylor series to estimate truncation error. We go back to the jumping problem. Now, it was the velocity that we'd like to estimate. And we have used an equation for that. And we said that another approach is to use the derivative, and then we said that the Taylor series can be used to determine the value of the function at any function, value of any function at any point if the previous values are given. So we can write then velocity at time instant t I plus 1 in terms of the velocity at time instant t I, using Taylor series. So this is the Taylor series. Simply here, you imagine that this difference is h. So this was fxi plus f prime xi times h. So you remember the previous equation. Now we can write the remainder at n1. So we can take this v prime ti in terms of the values of the velocity at ti plus 1 and ti. Then the first term here is going to be the first order approximation. The remaining will be the truncation error. This truncation error comes from this formula. We can rewrite this. Simply R1 divided by TI1 plus TI. So simply H is the second order derivative of the speed at xi, which is the time instant, let's say, between the two time values in here. Then R1 divided by the time step can be written as, or will be having an error on the order of h, simply. That's for first order approximation.